In a previous video, we considered the responses of closed-loop feedback control systems to step inputs in either a disturbance or the set point variables. We did this using idealized transfer functions in which we assumed that the valve and the sensor acted instantaneously, and we found that when using proportional-only control, we had steady-state offset in response to step inputs. We suggested that the steady-state offset could be reduced by increasing the open loop gain, KOL, and that the open loop gain could in turn be increased by changing the controller gain, KC, making it larger. However, for real processes, valves and measurement signals do not occur instantaneously. Let's consider what happens when we have first-order kinetics for a valve and first-order kinetics for a measurement, and we combine those with a first-order process or disturbance transfer function. We'll write the servo transfer function in this example. Remember that the servo transfer function is the product of everything in the forward path between the set point and the controlled variable, divided by 1 plus the product of all of the transfer functions in the control loop. So now this servo transfer function is a little bit more complicated than it was before because we have time constants in the denominator of GV and GM. In order to put this into the polynomial form, we need to multiply the numerator and denominator by 2s plus 1, 5s plus 1, and s plus 1. And we find a transfer function that contains a third-order polynomial in s in the denominator and a first-order polynomial in s in the numerator. In response to a unit step input for the set point, the controlled variable in this case will oscillate. And at small values of the controller gain, these oscillations decay, but we have a large steady-state offset. For larger values of the controller gain, we can get closer to the final steady-state value, but the oscillations become larger. As we increase the controller gain to 15, now we have oscillations that grow in the time domain instead of decaying. We've made the controller gain too large, and we've made this feedback control loop unstable by selecting a gain of 15 for the controller. It's important for us to know what the stability limit is. That is, what is the maximum value of the controller gain that we could choose without making this process become unstable? The key to answering that question is in the roots of the denominator polynomial. And that same polynomial occurs in both the servo and the regulator transfer functions. Note here that the control loop kinetics are not very fast compared to the process kinetics. That is, the time constant for the valve and the measurement are about the same order of magnitude as the time constant for the process. So the valve and measurement kinetics cannot be ignored. For linear processes, recall that the transfer functions can be represented in the poles and zeros form. And for a step input, the output will have a partial fraction expansion that contains each of the poles in a term in the denominator. And the unit step input will also ensure that we have a constant over s term, which when converted back to the time domain will give us a constant and exponentials. Now, if any of these poles are complex, then the complex exponential terms will of course represent sine and cosine functions. Note here that the poles of the transfer function, that is, the roots of the denominator polynomial, are the terms that multiply t in the exponents. So this function is stable, that is, the output is bounded, only if all of the poles have negative real parts. If any one of these poles, P1, P2, through Pn, have a positive real part, then those will represent exponentially growing functions in the time domain, and the output will be unbounded. So we would say that the process is unstable. Plotting the poles of the servo or regulator transfer function in the complex plane provides us a graphical representation of 4 categorical behaviors. If the poles are negative and real, these will result in exponential decays to a final steady state in the time domain. This pole lies on the real axis to the left of the imaginary axis. On the other hand, a positive real pole is one that lies on the real axis to the right of the imaginary axis and represents an exponentially growing term in the time domain. Remember that roots of a polynomial that are complex always appear as complex conjugate pairs. That is, they have the same real part, and the same magnitude imaginary part with opposite signs. So a complex conjugate pair appears like this when plotted in the complex plane. If the real part is negative, that is, that complex conjugate pair is on the left of the imaginary axis, then this represents a stable pair of poles, which will give rise to exponentially decaying sine and cosine functions in the time domain. However, if a complex conjugate pair of poles lies to the right of the imaginary axis, then these will represent exponentially growing oscillations in the time domain, and the process will be unstable for any input. Now, real systems also have time delays that could make even otherwise stable systems unstable. In this analysis, we're not considering the time delays. We're only considering the roots of the denominator polynomial of the servo and regulator transfer function and how those roots affect the stability. Later on, we'll consider how time delays impact stability. Based on this analysis, we can establish what's called the Routh stability criterion. The Routh stability criterion is based upon the characteristic equation, where the characteristic equation is the transfer function denominator polynomial set equal to 0. In this case, we're talking about the servo or the regulator transfer function. The poles are the roots of the characteristic equation. If the characteristic equation is first order, second order, or maybe even third order, it might be possible to factor it by hand and easily find its roots. However, for higher order polynomials, we might need to find the roots computationally, for example, using the roots function in MATLAB, or perhaps plotting the polynomial and just looking for where it crosses the x-axis to identify the roots. This works well if we know all of the coefficients. But let's get back to the question that we had earlier. That is, what is the maximum controller gain that the system can tolerate before it becomes unstable? In this case, the controller gain is a variable, and we don't know what it is. If we don't know the controller gain, we cannot compute all of the coefficients of the denominator polynomial, and therefore we can't find its roots. If we don't know all of the coefficients of the denominator polynomial, we can use what we will call the Routh method to establish stability criteria. To use the Routh method, we need to write the denominator polynomial in this form, with the coefficients ordered in descending powers of s. The a sub n coefficient represents the highest power of s term, s to the n. Ordinarily, the denominator polynomial will have mostly positive coefficients. But if any one of these coefficients is less than 0, that is, has the opposite sign of the others, then at least one root of the characteristic equation must lie to the right of the imaginary axis. But if all of the coefficients are positive, then we do not know whether any of the roots might lie to the right of the imaginary axis. And so we can construct what's called a Routh array to evaluate the sign of the roots of the characteristic polynomial. To construct the Routh array, we're going to put the first coefficient of the polynomial in the upper left-hand corner, and the second coefficient immediately below it. Then we'll continue to fill out additional columns in the first and second rows of the Routh array using the rest of the coefficients in order, first in the first row and next in the second row. Then we move to the next column and fill out the first row and the second row, etc., until we have no more coefficients to add. Then we'll use formulas to compute the values in the rows below, until we've constructed n plus 1 rows where n is the order of the characteristic equation. To compute the element b1, we'll take the diagonal product of the elements in the first row and the row immediately to the right of b1 and find their difference, and then divide by the element an minus 1. So this product is an minus 1 times an minus 2 minus an minus 3, divided by an minus 1. Similarly, to compute the element b2, we continue using the first two elements in the first two rows of the Routh array, and we then select elements from the column 1 to the right of the element that we're computing, but we use exactly the same formula. So we cross multiply, take the difference, and divide by an minus 1. If we wanted to compute an element b3, we would run into zeros over here in the next column, so we can stop there. We only have elements b1 and b2 in the third row. Now we can go down and compute the elements of the fourth row. Now to compute the element c1, we use exactly the same formula, but we shift everything down by one row. So we take the difference between these two diagonal products and we divide by B1. Of course, now if we were to attempt to compute C2, we would again run into zeros. We continue following that pattern until we've reached the n+1th row. The Routh method says that all elements of the left column of the Routh array must be positive for the roots of the polynomial used to construct the Routh array to be negative. So we want all of the elements in this far left column to be positive. We can use the Routh array method to determine the stability limit on the controller gain. So consider a characteristic equation 10s cubed plus 17s squared plus 8s plus 1 plus kc. And we want to know whether this process will be unstable. But of course, we don't know kc. We get to choose the controller gain, and we want to choose a controller gain that ensures that this feedback loop will be stable. We can use the Routh array to establish stability limits. First, we put the coefficients into the Routh array, which requires only the first two columns and two rows because we have a third order polynomial, therefore we have four coefficients, 10, 17, 8, and 1 plus kc. Next, we use the formula to compute B1 by taking the diagonal products and dividing by the element 17. In order for this process to be stable, the coefficient B1 must be greater than 0 because it's in the left-hand column of the Routh array. For the element B1 to be greater than 0, we find that Kc must be less than 12.6. Now we can compute B2, but when trying to compute B2, we don't have elements over here in the third column, so B2 ends up just being 0. That's good. Now we know that any elements to the right of B2 in the third row will all be zeros, and we can ignore them. That allows us to move down to the fourth row. In the fourth row, we can compute the element C1 by taking our B1, which contains the unknown Kc, multiplying it by 1 plus Kc, and then subtracting 17 times 0. Remember, our B2 was 0. And since we're dividing by B1, which also appears here, this becomes simple. C1 is just 1 plus Kc. In order for the process to be stable, that element must also be greater than 0. So 1 plus Kc must be greater than 0, or Kc must be greater than -1. Now we don't have to do any additional rows because below this, the entire Routh array will all be zeros. So the first element in the third row and the fourth row provide us with two constraints that can tell us the range of values for the controller gain that will ensure that our feedback control loop is stable. That is, Kc must be greater than -1 based on this element, and less than 12.6 based on this element. Any controller gain selected between these values will ensure that the feedback control loop is stable. Now, we also know that in order for the process to provide negative feedback, the product of all of the gains must be positive. In this case, that's probably true when Kc is positive. So in reality, we wouldn't want to choose a Kc less than 0. Otherwise, the controller will take the wrong action, and although the response will be stable, it won't provide the negative feedback required to bring the controlled variable back towards its set point. To summarize, the Routh array is a computational method that can be used not to find the roots of the characteristic polynomial, but rather to find out whether they all have negative real parts. And if we have unknown parameters, like a controller gain Kc, we can also use the Routh array method to find stability limits for those unknown parameters. In the next video, we'll look at another method that we can use to analyze the stability of closed-loop feedback control loops called direct substitution.